video, we're going to move on from chapter 2 and start looking at chapter 3, and give yourselves a pat on the back. You've finished pre-calculus. We are now going to start moving into calculus. And so the first big concept we're going to look at in calculus is limits. Okay, and to start us off, we're going to look at finding limits graphically and analytically. So you're probably asking yourself, what is a limit, right? You've probably heard it used in regular terms as something that's a barrier or a cap on how far you're willing to go. And that's kind of very similar. Essentially, what a limit is it's a word that's used in math to describe a time where a function gets really, really, really close to a number but doesn't actually touch it. So it gets infinitely close. So the distance between where you are and where you want to be is so small we can't even measure it. And we then say that that's the limit. That's our final point right there. That would be the limit. But we also have to look at the more formal definition, which is that let f be a function defined in an open interval containing c, except possibly at c. So c is a number, okay? So you've got a function f of x, that's why we talk about them, and a number c. And let L be a real number, okay? So c and L are real numbers. The statement limit, so that's what the LIM means, as x approaches c. So I'm here on my definition right here. So limit as x approaches c of f of x is equal to L. So basically it says as we get closer and closer and closer to that number c, our function is going to be equal to our limit, or L. And this means that for each epsilon greater than 0, there exists a delta such that if the distance between x and c is in between 0 and delta, so it's really, really small, because we can make delta super small as long as it's greater than 0, right? Then f of x minus the distance between f and L, the value of f at x and L, is less than epsilon. Okay, so that's the formal definition of a limit, and it's really just a way of describing how close we can get to a function value as we approach that x value. So let's look at an example of graphically finding a limit. So we've got the example is limit as x approaches 1 of x squared plus 2. So I've got the graph of x squared plus 2 here on the screen, and I'm approaching 1. So I need to figure out where x is equal to 1. That's going to be right there. Okay, so that's x equal to 1. So I'm looking at x approaches 1 of my function. So I'm actually looking at as I approach this point right here in the middle. Okay, now as I approach 1, here's a nice analogy to think of when you're thinking of looking at limits graphically is, do the cars crash? That's the question you have to ask yourself. And the reason why I say this is because when you're driving, right, you're on two separate sides of the road, but if the cars crash, they meet in the middle. And what's important about limits is that the function has to approach that point from both sides. So it has to approach from the right side and from the left in order for that limit to exist. So the cars have to physically crash in order for this to happen. So that means that if we were to run them into each other, they meet. So looking at this graph here, we notice that as we come from the left side, we go towards 3, right? And as we come from the right side, we go towards 3. They're going to meet each other at 3 as we approach 1. So my limit is going to be 3. Let's look at a different graphic representation of limits. We've got limit as x approaches 1 of f of x, where f of x is a piecewise function given by x squared plus 2 when x does not equal 1, and 1 when x equals 1. So I've graphed this for us. We have our curve of x squared plus 2, but notice there's a small little hole right here at 1, at 3, right? Because the function doesn't exist there. Instead, it's down here at this point 1. Now, at first glance, you might say, well, there is no limit because the cars don't crash because there's a hole in the graph. But that would be incorrect, okay? Think of a pothole. Does a pothole stop your cars from crashing? The answer is no. Your car is still going to run into that pothole, right? Presumably hoping that pothole is not super huge. So what we've got is we still do the same thing. We look, do the cars crash? So we come in from the right and we come in from the left. And yes, they do meet at that pothole. So the value of the limit as x approaches 1 of f of x is going to be 3 still. So a hole in the graph does not necessarily mean there is no limit. Let's look at one more. This time we've got limit as x approaches 3 of 1 over x minus 3. So my graph's going to be a little different. Notice it's a rational function, which we just took a test on today. And I've graphed that below. And we've got our two curves, just like you would for a rational function, with a vertical asymptote at x equals 3. So I'll draw that in. Okay. And we want to know what's the limit as x approaches 3. So again, do the cars crash. So as we approach from the right, we follow our function and it goes up, right? And as we approach from the left, we follow our function and it goes down. Are those cars ever going to run into each other? And the answer is no. So here, the limit does not exist, or DNE. Okay, so using cars to think, do the cars crash on a graph? That is probably a lot easier to begin with for the graphs, okay? The last thing we're going to do is look at limits analytically. Now, analytically just means we're going to solve the limit. And to begin with, limits are actually pretty easy. All you're going to do is plug in the number you're approaching into the function you're given. So let's start off looking at our first example on this page. We've got limit as x approaches 4 of 4 minus x over 2. So it's just like if I had asked you to find me f of 4, you'd plug in 4 everywhere you see an x. It's the same thing. I'm going to drop my limit notation and plug in a 4 every time I see an x. And so I get 4 minus 2, so my limit is 2. If we look at the next one, we've got limit as x approaches 5 of x squared plus 4. So again, every time I see an x, I'm going to replace it with a 5 and drop my limit notation. Limit notation is just LIM with the x arrow number underneath. Plus 4 equals 25 plus 4. This is 29. Okay, then we look at our next one. We've got limit as x approaches 2 of negative 1. There is no x to plug in. And it's like I said, if you had y equals negative 1 and I wanted y at x equals 2, it's still negative 1, right? Because y is still negative 1 for no matter what x value I have. So my limit is just negative 1. Next, let's look at limit as x approaches 4 of square root of x. So again, I'm just going to substitute in 4 for x. And so I get 2. And lastly, limit as x approaches 3 of the absolute value of x minus 3. Again, I'm just going to plug in that 3 into my function. So I get 3 minus 3 in absolute value bars. This is absolute value of 0, which is 0. And that's it. Okay, so we'll continue this lesson on Monday. We'll go on further into 3.3, which is more analytical solving for limits. And if you have any questions, please compare them on Monday.